All right, everybody should have gotten a message that it's recording. Things are going much smoother than they did last class. And we're going to get into something called the trigonometric functions, the trig functions. And yeah, oh boy, you all see word functions and all I ever hear about. We need to strengthen their knowledge of functions and so on. And that's that whole f of x. And most of you don't get it, and that's fine. I'm going to hopefully clear that up, make it a little easier as we go. But before we begin, we're going to start with the ever popular Pythagorean theorem. I think that dates back to this guy who was a really smart mathematician, Pythagoras, and he came up with this. There was even a Pythagorean society, but that was for men only. So we don't really have that today because men were the only ones allowed to be educated and all of that history. And something that comes from the Pythagorean theorem is the distance formula. And a couple of you are going, yeah, no. All right. Well, let's start out with taking a look at a triangle. And as soon as I draw that little box in my triangle, what do I know about the triangle? It is a 90 degree or right triangle. Yeah, we're gonna work a lot with right triangles early on, and then later we're going to get into triangles where one of them is not 90 degrees. They're all three different crazy ones. Well, this Pythagorean theorem is actually pretty good because I know contractors that use it all the time, and they have memorized something called a Pythagorean triple, and we'll get to that in a minute. But let's talk about pieces of a right triangle. Okay, I have two legs. The legs are A and B. Okay, they're the sides that touch the 90. They're going to be the smaller sides. C is the hypotenuse. It's the longer side. And if I have a right triangle, the Pythagorean theorem comes into play as A squared plus B squared equals C squared. A squared plus B squared equals C squared. And everybody was happy because this formula makes sense. And one of the, as I mentioned a while ago, I had a guy call me not too long ago, well, maybe about 3 or 4 years ago. He said, I'm trying to make sure the corner right here is square. And he said, what is the Pythagorean thing? And I said, well, the easiest one is this is 3, and this side is 4. What's that make the hypotenuse? Well, I'm going to 5, yeah. And that's one a lot of people have memorized. This is 5. And if you check it out, I quickly, or whoever figured that out, said, all right, leg 1 squared plus leg 2 squared equals the hypotenuse squared. 9 and 16, that equals 25. That equals C squared. So C must be 5. So then what he does, and he said, that's right, I remember. He takes his ruler and he'll measure over 3 inches or 3 feet, put a mark. Then he'll measure up this way and put a mark after 4 of the same inches or feet, whatever we're doing. Then he'll measure this and adjust this corner until it's 90 degrees and this length is 5. And if it fits that mark 3, that mark 5, and his 4, excuse me, and his ruler now hit 5, he was going, yep, nail that. It's because he was building a sandbox for a tree fort and everything in the sandbox underneath. That's how he measured to make sure that worked. So this 3, 4, 5 is a really popular Pythagorean triple. Why? Because there aren't any decimals in there. There aren't any decimals. All right, well, here's an example. This length, this point is the point 815. I go over 8. I go up 15. What is the hypotenuse? Oh, let's see, laddie. 8 squared plus 15 squared. And again, I'm trying to find the hypotenuse, and the hypotenuse is always over there on the right side. Okay, good.
17.
17. So I'd square this and get 64. I'd square this and get 225. Yeah, this is actually another Pythagorean triple. 8, 15, and 17. Okay. And here's how I found it. Now, I'm going to piggyback on that and say, well, if I started here and I wanted to go out to that point, that's the distance I'm covering. That's the distance I'm covering. So that's where Pythagorean theorem and the distance formula are buds. They stick together. So if I had another triangle, I'm going to draw, and I'm going to use the same one, but I'm going to draw it over here. This guy right here is going to be the point 8, 0. Up here, this guy is going to be the point, what did we have? 8, 15. And I want to find this. So the distance formula says, well, how long is this guy right here along the x-axis? Well, that's my 8 squared, right? How long is this guy from 0 up to 15? Ah, okay. So how do I find that? Well, the distance formula is going to be, instead of c squared, d equals the square root. Right? All I did was take the square and bring it over there. Now it's something squared, my A, and it's something squared, my B. How did I find this length? 8 minus 0. And that's where that x2 minus x, oh, we're getting crappy here. Distance equals square root of x2 minus x1 squared plus y2 minus y1 squared. All right, that doesn't make much sense. I know, right? So let's pick a point. I got 1 point, 1 comma 2. I got another point. I'm going to stay over here in this first quadrant. This is the first quadrant. I'm going to stay over here. Another point, 4, 7. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. What's this guy called? This horizontal thing. It's called the
x-axis.
X-axis. Perfect. Now, question that I still, to this day, have not had a student answer because no one ever taught them. Why is it called the x-axis? Nothing. I'll tell you why. In calculus, you're going to work with shapes that might look like this. And then all of a sudden, I'm going to take this and I'm going to rotate it and back up. I'm going to rotate a circle around the x-axis. What do I get? A donut. So now all of a sudden, instead of 2 dimensions, I start rotating around an axis and I get my 3rd dimension. Ah, I rotated around an axis. I could rotate this around the y-axis if I want. But that's where that comes from. Anyhow, 1, 2, right there. Whoop, there it is. 4, 7. 1, 2, 3, 4. Okay. 1, 2, 3, 4, 5, 6, 7. There. So this first point is the point 1, 2. The second point is the point 4, 7. What is the distance between these two? I'm going to draw my triangle. Let's get ready to rumble. I just drew my triangle. It's a right triangle. This guy is at 1. This guy is at 4. How long is that bottom piece?
3.
3, right? How did you get to 3?
4 minus 1.
Yep, and there it is. Whoop, there it is. The distance equals the square root of. I found this a squared, right? We were calling this a. How did I find it? 4 minus 1. 4 minus 1 and squared it. The same's going to happen here. This guy was my b. He's going to be a length of 5 because I took the y value minus the y value. 7 minus 2 squared equals the square root of 3 squared plus 5 squared equals the square root of 9 plus 25 equals square root of 34. Square root of 34. That's that distance. So that's the distance formula. Now you know the rest of the story. Questions? Again, if I bring this square over, you know, this distance, that's my hypotenuse. That was my c squared. If I brought that square root over, this was my A, this was my B. Somebody say, oh. Oh. Okay, so we're continuing along. We have our degrees that we've talked about in the first section and so on. Now we get into some things we have that, you know, all this stuff over here about the Pythagorean theorem and the distance formula. I like to make blocks because it makes things stand out. Looks pretty good, right? All right, thank you, Thomas. All right, so coming up next, we have the 6 trig functions. 6 trig functions. There's 6 of them. Good Lord. Yes, there's 6 of them. And where do the 6 trig functions come from? Well, let's see. I'm going to make a triangle. Oh, man, that is just awful. Let's try that again. I'm making a triangle, and I have an angle measure here. And we're going to use angle measures like alpha and beta, and we're going to use a bunch of different Greek names for it. But I have an angle measure right here. I'm going to call it theta. Theta. Circle with a little squiggly through it. And as long as this is, again, a right triangle, I can talk about a lot of stuff in this right triangle. When I do, I talk about the 6 trig functions. And a lot of you know what they are. You've had them in geometry. You've heard about them. But the 6 trig functions are the sine of theta, the cosine of theta, the tangent of theta. Then we have 3 more, the cosecant of theta, the secant of theta, and the cotangent of theta. So far, so good? Good. So we're gonna go back to calling this A, B, and C again, and you'll see them listed. Some people will call this X, you know, and I think our book uses X, and they call this Y, because this is the X-axis and this is the Y-axis, and you'll see the letter R come in here. Why we're not being consistent, I don't know, but we have X, Y, and R. And the sine is going to be, oh boy, I forget. Oh, I know, I remember it this way. What's that famous Indian's name?
SOHCAHTOA.
Yeah, SOHCAHTOA. SOHCAHTOA. I have the S for sine, C for cosine, T for tangent. These fellows are just sitting down here right now. We don't need to talk about them. They just confuse us a lot. But anyhow, I have these. I have O, which stands for opposite. And I have an H, which stands for hypotenuse. And I have A, which stands for adjacent. Adjacent. So when I look over here at angle theta, its opposite is Y. Its adjacent is X, and its hypotenuse is R. So if I use SOHCAHTOA, I know it's going to be opposite over hypotenuse, Y over R. Oh, cool. Cosine, adjacent, which is X, over R. Tangent, opposite over adjacent, Y over X. So yeah, I'd be willing to bet everyone, if not almost everyone, has heard of SOHCAHTOA. And if you haven't, learn it quick because it's going to help you a lot. Now, these three have a name, this group of angle measures here. They're called the reciprocal functions. That's a C, that's reciprocal functions. And how do they work? Well, the cosecant is the same as 1 over the sine, which means I'm taking the reciprocal of this. So this actually becomes R over Y. What you'll remember more than anything is up to this point. The cosecant is 1 over the sine. The secant is 1 over the cosine. And the cotangent is 1 over the tangent. So we have the whole SOHCAHTOA going on. We have our three main trig functions. And then we have what we call the reciprocal functions. Cosecant is the same as secant. This one's a C, that one's, yeah, I know it, secant, and so on and so on. Put that in your vault of things to remember to help us to use it later. Let's see, I'm checking the chat. Nothing's in the chat. We don't have any questions yet. We're moving right along. Das good. All right, let me get back to my original notes. We now know what the trig functions are. They are sine, cosine, tangent, cosecant, secant, and cotangent. We refer to those as of an angle measure. You know, like over here, here's my angle measure in a right triangle. Now I want to have a problem. Let's see what we can solve here. I want to take a given point, -3, -4, 1, 2, 3, 1, 2, 3, 4, and I have that point. And I want to know what are the 6 trig functions for this point. So how do I do it? Well, whenever we take a point, we draw the triangle according to the x-axis. Okay, we'll always touch the x-axis. So this is the triangle. If it was a point here, it would be down to the x. If it was a point over here, it would be down to the x-axis. So this is now where my mysterious theta is. I don't know what it is. I can't figure it out. Eventually I will be able to, but right now you don't. Let's see, what is this side right here? Well, it's hard to ask you what its distance is because distance is always a positive number. But if I look at this, what is the location might be a better word. This guy is -3. This guy is -4. So if I want to get ready and find the sine of theta, so SOHCAHTOA. I need to find the hypotenuse yet. All right, how do I do that? -3 squared plus -4 squared equals, we're going to call that R squared. 9 and 16 is 25.
5.
Hey, yeah, that's going to be R squared. R equals 5. Thank you. So that's a 5. So now that I drew the triangle, it's going to be a lot easier to find the sine of theta. Opposite over hypotenuse, -4/5. Yay. So whatever that angle measure is, okay, whenever we deal with angles, we start on this horizontal axis, go through the first quadrant, around to the second quadrant, over through the third quadrant, and into the fourth quadrant. How far around is it? If I made a circle, in as far as degrees are concerned, how far around is it?
360.
Excellent. 360 degrees takes me all the way around. If I went from this horizontal axis up through quadrant 1. That would now be 90 degrees, 180 degrees. And then I start coming down into here. I'm looking at maybe 200 degrees, 210, 220. So that theta, when I learn how to find out what it is going to be 180 plus a couple of more degrees over there. What is the cosine of theta?
Opposite over hypotenuse.
The cosine, adjacent over hypotenuse. Adjacent, so here's my angle. Adjacent is the leg beside the angle. That's going to be -3 over hypotenuse. Finally, the tangent of theta is going to equal opposite over adjacent.
4/3.
4/3. Yepers. Good. And now if I wanted to keep going, the cosecant of theta, flip it, -5/4. The secant of theta, flip it, -5/3. And the cotangent of theta, 3/4. Want to try another one?
I'm pretty comfortable with it.
I did get a yeah. So let's do. All right, I'm going to take a point. -2, 4. What are the trig functions for this? I recommend you draw the triangle. You're going to hear me say that a lot throughout this semester. Start by drawing the triangle. Yeah, I need to use that distance formula. -2 squared plus 4 squared equals r squared. 4 and 16 equals r squared. 20 equals r squared. R equals the square root of 20, which is the same as the square root of 4 times 5. R equals 2 square root of 5. Are you jiggy with that? Let's do the big 3. What's the sign? So
4/2√5.
4/2 square root of 5. And we all know that we can't leave that. So I'm going to rationalize it. Going to multiply the top and bottom by that square root of 5. The numerator becomes 4 square root of 5. What's the denominator become?
$10.
Yeah. Square root of 5 times the square root of 5 just becomes 5. 2 times 5 is 10. And then I have to simplify it. Goodness gracious. 2 square root of 5 over 5. Better leave a little more room this time. Cosine of theta. So adjacent over hypotenuse. -2/2 square root of 5. And again, I'm rationalizing it. -2 square root of 5 over 10 again. negative square root of 5 over 5. Tangent.
4 over negative 2.
Good. 4 over negative 2, which is nice and simple, and it's negative 2. All right, so I did that for a reason. And the reason is I'm going to take a look at, oh, 2 of these are negative. I'm in quadrant 2. And when I do an angle in quadrant 2, what is actually the only one that's positive?
Professor?
Just the sign, right? The sine's positive, cosine's negative, tangent's negative. So the only one that's positive is the sine. This example we did over here, which one was positive? This was for an angle that's in quadrant 3. What's positive? Tangent. Just the tangent. So down here in quadrant 3, only the tangent is positive. Huh. What do you think it's going to be for quadrant 1? Well, if I think about a point over here.
Cosine.
No, if I think about a point over here, you know,
All 3 of them.
All 3 of them, right? So they're all going to be positive. Who's positive? That's the question. It's a game show. Welcome to Who is Positive?
Professor?
Yeah.
Can I ask you a quick one? On the cosine.
Here?
Yeah.
Okay.
The result.
Yes.
Negative 2 into 10. Is it not supposed to be negative 5?
Well, let's see. I go, well, this is supposed to be square root of 5 right there. So square root of 5 over square root of 5. It's called rationalizing the denominator. I get negative 2 square root of 5 over 2 times, that becomes 5. Square root of 5 times square root of 5 becomes 5. So 2 times 5 is 10.
Yeah.
I cancel. I think I'm okay with that.
I'm talking about the simplifying. When you simplified negative 2 over 10, is it not supposed to be negative 5? Yeah. The negative 2 into 10.
Yeah, that becomes 1 over 5. So this should just be a 5. 2/10. If I reduce that, that's the same as 1/5.
Okay. I was looking at it from negative 2 over 10.
Okay. Okay. Yeah. But it's going to become a 1/5. So that just is the square root of 5 up there. The negative stays. Yep.
Okay.
So now I'm down here. All of them are positive. And this is something that later is going to come out and then pay dividends. I noticed that only the sine is positive over here in quadrant 2. The tangent is the only one positive in quadrant 3, which means what's going to happen in quadrant 4? What's left?
Cosine.
The cosine, right? As I said, we always go counterclockwise. And oh, if I had to memorize that, go ahead. What's somebody have for me? There's one saying that says all students take calculus. All S, T, and C. That's one. One I like is all spiders taste crunchy. But this is all about what's positive. Thank you. Thank you very much. I'm performing every Monday at 9:30 online. Yeah, so if I need to know what's positive and what's where, a way to check myself, I'm gonna hang on to that little ditty that we just talked about. Cool. What else we got? Oh, we already talked about. Here's another example. I'm throwing stuff everywhere. Good one. Yeah, I have this, and I say, what the heck is this? Calculate the 6 trig values, and x is greater than 0. That means I'm going to draw that line. And, you know, how do I draw a line? Well, I can pick 2 points. I can do all kinds of stuff, but I'm going to draw a line. Let's see. If I say X is 0, what's Y have to be?
0.
0, good. If I say X is 2, what does Y have to be? Plug 2 in, subtract 2, divide by 2, Y equals?
-1.
Excellent, -1. So now I know a point on this line, 0, 0, that's good. I know another point, +2, -1, and I draw my triangle. Whoop, there it is. Again, this guy's going to be in my right angle. Here's my 2. Here's my -1. 2 squared plus -1 squared equals R squared. R equals?
√5.
Square root of 5. So now that I know that's the square root of 5, I'm going to be able to find the sine. And again, theta is right here. Sine, so opposite over hypotenuse, -1/2. No, excuse me. Opposite, oh, don't look. -1 over square root of 5. I have to rationalize again. I get negative square root of 5 over 5. Cosine, opposite, -1 over square root of 5. Finally, tangent, opposite over adjacent. Tangent is -1/2. All right, so last one I want to talk about in this section is these quadrantal angles, the quadrant angles, okay? What if I don't end up in a section, but I end up right on, so instead of giving the point up here to -1 to draw it out, what if I'm given the point 1, 0? What if I'm given the point 1, 0? Well, let's see. If I'm given the point 1, 0, what's my X? How far over did I go to that point right here?
1.
Yeah, it's 1. So, this is kind of a funky looking triangle kind of idea, but I went over 1. How far did I go up? Well, it's actually going to be this Y value of 0. So it didn't go up very far. Finally, what's my R? Well, 1 squared plus 0, it looks like that's going to end up being 1 as well. So for 0 degrees for that point, I have something that looks like that. If I said, again, what's the sine here? Well, the sine is opposite over hypotenuse. 0 over 1 is 0. Which, I'm now back on, that's actually 0 degrees. The sine of 0 degrees equals 0. What if I did the sine of, not the sine, the cosine of 0 degrees? Again, this guy right here is 0 degrees. Didn't go up anywhere. It's that point. What's the cosine of 0 degrees?
1.
1. And what's the tangent of 0 degrees?
Is that undefined?
Well, it's opposite over adjacent. It's 0 over 1, which is going to give me a 0, just like the sine did. So I can do all these for 0 degrees. What if I said for 90 degrees? That's this point. What's my X value? Right here out of the ordered pair. My X value is 0. My Y value is 1. And my R value is going to be 1 again. Again, these are my 4 special angles. 0 degrees, 90 degrees. I keep going around. 180 degrees and 270 degrees. So if I asked you, what's the sine of 90 degrees? You know, again, that would be like drawing this triangle where it's the 0.01. So I go up 0. I mean, I go over 0 and I'm going up 1, and that's a 1. And same kind of idea. But I do know it is, well, let's see. If I took this triangle, this is going to go back to being beneficial a while ago. This is theta. This is x. This is y. This is r. The sine of theta was y over r. So if I look back up here, what's y over r? 1. Cosine is x over r, which is going to be 1. The tangent is y over x, 1 over 0. And now this is what somebody mentioned a moment ago. It's going to end up being undefined. Questions? Is that clear? Is that clear as mud? I'm taking that to be as clear as mud. All right. 1.3. Check this out. All of my babbling, we already know what the reciprocal identities are. 1.4. The reciprocal identities. The sine of theta was the same as 1 over the cosine of theta. Can I get a Yahoo? Yahoo. Yeah, thanks.
Yahoo.
The cosine of theta equals 1 over, oh, wait a minute, don't Yahoo me, we did this wrong. What's that supposed to be? Sine of theta is the same as 1 over
Cosecant.
cosecant. Thank you. Cosine of theta is 1 over the
Secant.
secant. Yeah, they're reciprocals. Finally, the tangent of theta equals 1 over the cotangent. All right, calculate the cosine of theta given the secant of theta is 5 over 3. Find the cos. Find it. Is it lost? No, it's not lost. It's not lost. Calculate the cosine of theta given the secant of theta equals 5/3. Oh, look. All spiders taste crunchy. All students take calculus. Yay. Cosine of theta. Find the cosine of theta given the secant of theta.
Is it just 3/5?
Absolutely. The cosine of theta is going to be the same as the reciprocal of the secant. So it's going to, in fact, be 3/5. Cool. So then this guy, the sine of theta is going to be
Over the square root.
Yeah, 2 over the square root of -12, which is, I need to multiply, I need to rationalize top and bottom by the square root of 12. A little work to do here. Equals 2 times the square root of 4 times 3. What's the square root of 4 become?
2.
2. 2 times 2 is 4. So now I have 4 square root of 3 over -12. All right, I think I got an answer. Negative square root of 3 over 3. So using those reciprocal identities, I want to always keep these in. I'm adding these to my inventory. So I'm starting to put together a nice little inventory of these things called identities. So if I ever have 1 over the cosecant of theta, I know it's identical to sine of theta. I can rip that out. I can put the sine of theta in. Kelsey, welcome to the big show. What do you got?
I have a question.
Yes.
Why, for finding sine given cosecant, why didn't you stop it at 2 square root of 12 over negative 12? Why did you like expand it more to square root of 4 times 3?
Well, there's this thing in the world. It's called simplify. And everything you do and everywhere you go, they want you to simplify. So can I reduce this fraction? The answer is yes. First thing I'm going to do is reduce that square root of 12. I mentioned up above, that's the same as the square root of the product 4 times 3, which I can then break apart into the square root of 4, square root of 3, which becomes 2 times the square root of 3.
Gotcha. Okay, thank you.
Yep. When I take that bad boy and plug it back up in there, I get 2 times 2, 4 square root of 3 over negative 12. Good question. Uh-oh. Let's do 1, maybe 2 more things. See what we got. Oh, we can't see it. We can't see it. Now I can see it. What's the quadrant? All spiders taste crunchy. All spiders taste crunchy. What quadrant is theta in if the sign is positive? Okay, which 2 have the sign positive? Quadrant 1 and quadrant 2. The sign will be positive in both of those. But now the tangent is negative. Answer is quadrant
2 and 4.
Nah, because up down here, only the cosine is positive.
But
I only
wait.
want the sine to be positive. So sine is going to be here. Sine, cosine, and tangent. Yep.
Sorry, I thought you said tangent less than 0.
So the tangent is going to be negative. So if over here I go with the sine positive, what's that mean the cosine and tangent are?
Negative.
Yeah. This is the only one that's positive. The cosine is negative and the tangent is negative.
Right. So for the second part, tangent of theta is less than 0 is 2 and 4, right?
Right. So for that question, it's 2 and 4, but I want both of these. So I should maybe put an ampersand there. Okay, I have to fit both. And because we only have 1 theta. There's just 1 theta. I understand absolutely what you were saying.
Gotcha. Okay.
What's the quadrant if the cosine of theta is negative and the secant is negative? Secant's the same as 1 over the cosine, right? So these both kind of go hand in hand. What quadrant is the cosine negative in? Cosine is negative here. Cosine is negative here. Quadrant 2 and quadrant 3. Kelsey, another question?
Oh, no.
Oh, you still had your hand up. That's why I didn't. There you go. Cool. All right. Just a little taste. Last problem. Whew. Full load today. I did a lot of talking, and I don't like doing a lot of talking, believe it or not. Right here. See what we can do with that. Determine the values of the trig functions given 1 value and a quadrant. Okay. Theta is in quadrant 2. Sine of theta is 2/3. What's the first thing I'm going to tell you to do? DTT. I just made that up.
Draw the triangle?
Draw the triangle. DTT. That's my new name. I'm going to use that when I text somebody today. I'm going to put LAM or LMAO. My students had the DTT. Unless that already stands for something I don't know. I think if you change one of those letters, it can become pretty crude, but I don't know. Theta is in quadrant 2. Theta is here. There it is. And I have something going that looks like that. Okay. Sine of theta, sine, so, ka, toa, is 2/3. Opposite is 2. Hypotenuse is 3. Uh-oh. I need a leg. Sounds like I'm a Kentucky Fried Chicken. I need a leg. I need this value right here. How far over did I go y-wise?
√5.
I hear a √5. I'm going to just write that over there. Again, it's this guy, x squared plus y squared, which is 2, equals r squared, 3 squared. X squared plus 4 equals 9. X squared equals 5. Hey, I like that square root of 5. X equals square root of 5. Oh, so close.
Oh, negative.
Excellent. Excellent. This is negative square root of 5. By location, the coordinates of that point are negative square root of 5, positive 2. So this is an important problem, and you can see why. This has to be negative 5. Even though our Pythagorean theorem always gives us a distance as a positive, we're doing more about location. And last week, your location was at your home. My location was in Key West. So I was suffering through my first week of classes teaching out of Key West. No, don't give me your finger gesture. I don't appreciate that. Just kidding. Yes, Jephthah.
How did you get negative square root of 5?
Okay. So I'm taking a triangle. And I know that this guy is 2 and this guy is 3, and I need to find this guy right here. I'm going to call him X.
Okay.
So do you understand how I found X?
Yeah.
Okay. A leg, and a hypotenuse. X squared plus 2 squared, a leg, and a hypotenuse. So I got the square root of 5. Now, if I drew a point over in this quadrant, you're going to say that its coordinates might be 1, 2, 3, 4, 1, 2, 3. Its coordinates might be negative 4, 3, where that distance traveled, and again, I don't like to use the words distance because distance is always positive. That's over negative 4. This is up positive 3. So this point right here has the coordinates of 2 negative square root of 5. Excuse me. Oh, don't look at that. Don't look. Excuse me. Square root of negative 5, comma 2. Because I came over this, I went this direction. Square root of negative 5. Then I went up 2. So that's this guy's coordinates. So by location, I knew this had to be square root of 2. If it were square root of 5, negative square root of 5. If it was positive square root of 5, if I had the point square root of 5, positive 2, I'd have to go this distance, square root of 5, and then up 2. That would be that point. But by location, the X value has to be negative square root of 5.
Okay, I got you.
So now that I have theta, it's going to be easy to find the cosine. Cosine of this here theta, adjacent over hypotenuse, square root of negative 5 over 3. And the tangent. So katoa, opposite 2 over negative square root of 5. And again, we'd have to rationalize that. Multiply top and bottom by square root of 5 and get 2 square root of 5 over 5. Negative 2 square root of 5 over 5. Whoo! That was a lot of stuff put in the inventory. This is a big one right here. Draw the triangle. All spiders taste crunchy. All right, so we're going to stop there. No, that's good because we're almost out of time. And as you can see, we have some more here and some more here to talk about in section 1.4. But before I run out, are there any quick questions from what we covered today? 1.3, 1.4. A lot of good stuff. Yes, Patrick.
So this is based on the worksheet. What exactly is a coterminal angle?
Okay, coterminal angles are angles, good question, are angles that finish at the same spot. So if I drew a 45-degree angle, here it is, whoop, there it is, 45-degree angles. And this is its terminal side, where it stopped. Can you give me another angle that has this same 45 degrees? Well, I went 45 degrees and stopped. Here's another angle. Check this bad boy out. 90, 180, 270, 360, and another 45, 360 degrees, plus that actual 45 ended at the same place. So 45 degrees and 405 degrees are coterminal. They end at the same spot.
Okay, so for like number 9, you would just do 871 minus 720 and
Yes.
get an answer of 150.
Right.
150.
Or
Right.
you could just, what was the number again? Number 9 is 871. You could go, well, let's just subtract the 360 degrees. And I get 115. So that would be another coterminal angle. It's just going around one. I could subtract another 360 degrees, which is where you got your 720, 151. So all of those end at the same terminal side.
Okay, I got you.
Just keep going around and around and around and around and up and down and a 1, 2, 3 twist. Other questions?